Hello viewers, welcome to this course on mathematical modeling. So in this lecture, I will tell you that once you are ready with your mathematical model, then how you can solve this mathematical model numerically. So I will let you know that how you can apply the numerical techniques to make the algorithm, and then we'll try to make a code that is MATLAB code based on MATLAB or Octave, because some students might not have the MATLAB in their computer, so they can download the free software Octave. So that is just a copy of the MATLAB, and every command whichever is applicable in MATLAB will also work in Octave. So let's start that how we can deal with this one. By the way, I am Dr. Vivek Kumar Aggarwal, working as a faculty in the Department of Mathematics, Delhi Technological University. So I will share. Yeah, so I will just give you a very simple method, that is Euler methods, that how we can find the solution using the Euler method. Because you know that, like, suppose I take the population model. So this is, suppose I take the population model, that is n dash t is equal to some growth factor r and then the nt. So this is a simple growth model with some initial condition. At t is equal to 0, it is some value and naught is there. So in this case, this is a ordinary differential equation, and I want to solve this ordinary differential equation using some numerical methods. So the first method we always deal with, and is a powerful method, that is called the Euler methods. So in the Euler method, it is a first order Taylor series method, is known as Euler method. Only the constant term and the linear terms are used in Euler method, and the error due to the use of the truncated Taylor series of order h square. So in this case, this method is, we know that this is a linear method and its order of convergence is h square. It means that if you are able to solve the given OD, and if the solution of the OD is a linear function, then this method is going to give you exact solution for that one. Now, so I will just give you briefly that how we can find out the Euler method. So I know that if I have a function, so suppose this is my function y, and I apply on x naught. So x naught is some factor there, x naught plus h. Then I can expand using the Taylor expansion. So this becomes y x naught, and then h dy by dx at x naught y naught. And I take all the other terms, that is just a factor of order h square, because we know that it is going to be y at x naught plus h, then y dash at x naught, then h square by 2 factorial y double dash x naught, and then h cube by 3 factorial y triple dash x naught, and so on. So what I will do that, I will just keep the first two terms here. So you know that this is a just the linear function, and then I will take my h square common from all, and I will remains with these terms, and then these terms I can write in the terms of y at x naught plus h y dash at x naught plus order of h square. So all the terms is of order of h square. So this order is the asymptotic that notation that we already know. So I can write this Taylor expansion in this form. Now what do we do that? I will, so whatever we are going to do in this case, that suppose I have a y dash is equal to some function x And so in the terms of, I just write this function as dy by dx, and then I will write the function of x and y. And here I will just take the initial condition at x naught is equal to y naught. So this is my first order ODE, and in this case we want to solve it numerically. So in the numerically we are going to have the solution not for continuous time, so time is a x here, but we'll be able to find the solutions. So suppose this is the point x naught. So at this point the solution is known to me. Then with the help of this numerical solution, I will try to find the solution at this point, and then at this point, and this point. And we don't know what is the value of the solution in between these. So that is called the discrete solution we are going to have. So in this case, we are getting the value of xn is x naught plus nh. So if n is 1, we'll get x naught plus h, that is x1. So this becomes x1, then it is x2, it is x3, it is x4, it is x5, like this one. So in a sequence, we are able to find the solution of this first order ODE with the help of this Euler method. And what we are considering here, that yn and yxn, so it is approximately same, not exactly. So y at xn means I know the solution yx, and I substitute the value xn instead of x, and I will get this value. So at this point, suppose I already know the solution of a first order ODE. So suppose this is the solution of that ODE. So what I will do, that at x naught this value is that is known to me. Then at x1, if I substitute this value x1, so I'll get value at yx1. And on the left hand side, this function yn, that is the numerical solution we are getting at the nth iteration in this case. So suppose I will get y0. So y0 is exactly the value of the function at x0, because in this case it is known to me. Then y1 I will calculate from here, and this will be approximately same as yx1. y2 is also approximately same as yx2. It is not exact the same, because if this numerical method is going to give you the exact solution, only then it would be equal. Otherwise they are nearly same. So that's why in this way we can say that our solution is going to converge. So, and that this is my dy by dx. So dy by dx is my fxy that I have already here. So if you calculate all these things and substitute, then you'll get the Euler method. So Euler method is basically, it becomes, now this is my Euler method. So here the I is start from 0, 1, 2, 3, 4, and so on. It means when I put I is equal to 0, I will get y1 is equal to y0 plus hf x0 y0. And this value is known to me. So I will calculate the y1 here, and then y2, and then y3, and like this one. So this is the iterative method, because in iterative method means when we need a initial point to start the method, and then at every iteration we are going to get the solution. So this is called the iterative method. So the Euler method is an iterative method. Now I can write this method in this form. So we have a first order ODE. So this dot means it is a time, or maybe you can write y dash. So I have dy by dx is equal to fxy, and this is an initial condition given to me. Then determine if we know the solution, and then this Euler method gives you this. So Euler method is basically what we are doing is, if you remember, then this is a differential operator, and I can write its first order forward operator. So I can write this as a y at n plus 1 minus yn divided by h. So this is a forward operator, and this should be equal to f at xn yn. So left side I take this derivative, and on the right hand side I defining the function at xn and yn, and n I'm starting from 0, 1, 2, 3. Now I can write my fn plus 1 is equal to, I just take h on the right hand side. So this is yn h f xn yn. Now this becomes my Euler method, so like this one. So interpretation of the Euler method. As I told you that, so this is my y naught. The solution is given to me, that is the initial solution. Now I want to find the solution at x1 with the help of this. So I will get y1 is equal to y0, because I am substituting n is equal to 0 here, plus h f at x0 y0. So I will substitute value here, and then I will also know the value of this one. I will get y1. So y1 I'm getting Euler method, not from the exact solution. So from here, maybe I have y x and x1. Suppose my y1 I'm getting like the 2. I will get y1 plus h f at x1 y1. Now x2 and y1. So y1 I have calculated from this first iteration. x1 I know that x1 will be x0 plus h. So I substitute the value in this function, multiply by h, and then this becomes y2. And what is h here? So h is the distance between x1. We are taking the uniform grid, so my h is always constant. You see this, and this way we are finding the value. So the slope here is this one. Now my y1 is this. So y1 minus y0 become h f x0 y0. So this is my y1, this is my y0. So I take the, so the difference is equal to h f x0 y0. So from here we are able to find the value of the function at x1, that is y1. Now this is the way we can find y2. Now I am using this value here and then substituting in the Euler method, and I am finding my y2. So y2, if you take the y2 from here, and y2 minus y1 should be equal to h f x1 y1. Now this value we are calculating from Euler, this value we are calculating from Euler. So if you want to calculate the error, so error will be y at x1 minus y1, y at x2 minus y2, like this one. This error we are calculating, we can calculate. So this is the yx1 is the value of the solution at x1. So suppose my given OD has a solution, and that solution I can find out, then based on that solution, I will put the value of x1 in y, and then I will take the difference of the y1 which I have calculated from the Euler. So that will give you the error at the point x1. Similarly, we can find the error at x2. Now the question comes that if we are able to solve the given OD analytically, then why is the need of numerical solution? No, this one we are doing because whenever we develop a numerical methods, we always try to apply this on the problems whose exact solution is known to us. So we'll try these things on that function, and then we need to verify that our method is working on this type of problem or not. And then if we find that our method is working, only then we can apply for other type of problems which are very hard or very like a very difficult for to find the analytical solution. So this is the interpretation of the numerical method, and you can see from here that it just give you the solution here and then here and then here. So it is giving you a solution of linear type. Suppose your exact solution is like this one. Maybe suppose your exact solution is like something like this one. Then from here you can see that here this is the error we are getting. Here this is the error we are getting. So, but if your solution is a linear, then definitely it is going to be from this one, and then there is no error. But when if your solution is not the linear solution, then definitely we are going to introduce some error. Now we can apply this Euler method for a very simple OD. So this is dy by dx is equal to 1 plus x square, and this my initial condition is given to me. Now I want to find y at 1.01, 1.02, and 1.03. It means that I want to find 1.01, this value at 1.01. So now I start with my x naught here is 1, and my x1 I can take 1 plus h, and 1 is this one, so h is 1.01, so I can choose my h 0.01. So then it become my 1.01. Then x2 become 1.2h, so it is 1.02. x3 1.03, like this one. So here we are able to find the Euler method. So this is my function. So my function fxy is 1 plus x squared. So in this is a linear function, and that is always known to us. Now I'll substitute this value and find the solution. So this is my Euler method. So I will put the value of x naught. So x naught is 1. So it becomes minus 4 because the value is given minus 4, plus h is I have taken 0.1, and then I substitute here. So 1 plus x square, x is 1, so it will give the value minus 3.98. Similarly, I will take my y naught. So it depends upon my y1, and then I'll again the substituting here. So whatever the solution I'm getting, numerical solution, I will take that value here, multiply by h, and then 1 plus this value 1.01, so I'll get this value, and then I'll get this value. So you can see from here that I have from the first iteration I have calculated this value, y1 is equal to minus 3.98, and then I'm using this value to calculate value of y2. So in the y2 I'm using this value. So you can see from here that if some error has been introduced in y1, then this error also going to affect this y2. And then from y2 also we are using y3. So in this case, we are using the value of y2 to calculate the value of y3. So this error will grow, and this will also going to affect my y3. So in this case, you can say that if some error, the error is bigger in the first iteration, then it is going to be much bigger in the next iteration, and it may happen that your solution may not converge. So everything depends upon that what is my h, because if you take a smaller h, then this error may be going to be a small one, and that is not going to affect the solution too much, and your solution will converge. So in this case, that you can see that the error is also going to play the big role in the Euler method. So if I find out the solution, then you can see that this is my initial solution, and this is my y1, y2, and y3. Now I can find the true value. So true value means, so this is my x, yi, whatever the value I get, and true value of yi means this is y at xi. So it is y at xi, it is okay, the same, because it is a initial condition. Then at 1.01, this is my exact solution and this is my approximated. Then it is the exact solution, this is approximated. This is exact solution, this is approximated. So from here you can see that this solution, if you round off up to second digit, then it is going to give you the same solution as minus 3.98. In this case also, it is going to give you the exact solution up to 4 digits, like this one. Here also, it is minus 3.9394. So it is minus 3.39 or 9390. So it is going to give you the solution up to 3 digits, the same solution. Because if you just round off also, then it is also going to create the error at this 4th digit. So it gives the solution exactly up to the 3 digits. So this way we can calculate the value of the solution, and then we can also find the error. So error is, you can find the error this minus this, so that it gives you the error. And if you plot this graph, then the graph of the solution for h is equal to 0.01 is this one. So that is the solution we can find, because this type of graph we are going to plot with the help of MATLAB or Octave. So this is a type of errors: local truncation error, global truncation error, round off error, that we already know. That error due to the use of truncated Taylor series to compute this value in step 1, because we have truncated the Taylor series up to only first order terms. Global truncation error, accumulated truncation over many steps. As I told you that we are calculating y1 with the help of y0. So there is no error in y0, then we'll calculating y1. Then with the help of y1, I am calculating y2. So this is the accumulated truncation error over many steps. So that is going to happen. And this is the round of error, error due to infinite number of bits used in the representation of number. This error could be accumulated and magnified in succeeding steps. Because in this case, what we are going to do, whatever the solution we are getting from y1, that solution may have infinite number of digits. But in the computer, what we do, we just use, suppose, 5 digit of that number. So in that case, we have introduced the round of error. And then again, we are using this number to calculate the value of y2. Then again, we have rounded off the number. And again, the rounding error has comes into this calculating the value of y2. So this way, this rounding of error is always there whenever we do the computation with the help of computer. So rounding of error is always there whenever you are doing any type of computing, maybe in a computer or whatever you want to do. So that way we are going to have a different type of error in Euler methods. So I think now I should stop, and in the next lecture I will tell you that how we can make the code for solving population model, and then SIR model, and then again SIR model with vaccination. So that will continue in the next lecture. So thanks for watching this lecture. Thanks very much.